Because ammonium is not a transition metal.
Oh, it's so when it says three, it's three like the Roman numerals.
Yeah,
Oh,
this
okay.
would be chromium 3 because the
I
three
got you.
represents the charge
Right.
of the chromium. Yeah,
I was using periodic table online, and it's like a +4. One could also be -4, and I
yes.
didn't know like how would you know?
Okay. We're not going to use that unless, of course, at the very way down at the bottom.
Okay.
But carbon is to be consistent the first month or so of general chemistry, we look at carbon as being +4 or -4. It really isn't. It's what's called covalent in that it doesn't take electrons and it doesn't give up electrons. It does what it shares electrons. So by sharing, it isn't going to actually have a charge. But down at the bottom, way down there, we get down into lead and that, then typically write Roman numerals because they can have multiple charges. It does and it doesn't. It gets kind of confusing, right? Because
Yeah.
you think, why can't this just be consistent? Uh, it's really complicated. It just is. My father taught math and physics for 40 years. He hates chemistry, just hates it. Very smart man, but hates chemistry because of all these goofy exceptions. So he said, I don't like it. He likes math because no matter what, this is what it's equal to, right? This is physics. This is what it's equal to. But chemistry has all these little nuances, and it's just kind of frustrating at times. I remember in graduate school, probably one of the smartest individuals I ever met and worked with was my PhD advisor. Incredibly intelligent, such a nice guy, just so nice. Every time we sit down to do an experiment, he said, "Well, what do you expect is going to happen? What do you think is going to happen?" You say, "Well, we think this is going to happen, and this is kind of the interpretation." Or he would say that we were always wrong, always wrong. Chemistry can be kind of complicated in that regard. And I think that speaks to the genius of God. How are we doing on A? Got it? We have the chromium 3 sulfate. You can need some marker. Bless you. And so the chromium 3 sulfate, plus the ammonium carbonate. Well, carbonates typically are going to form precipitates, right? Remember that? So when I think of these, my mind always goes to the halogens, ammonium, and then the nitrates and acetates. Those are almost always going to be soluble. Does that make sense? It's kind of where my mind goes. And you got the carbonates and the sulfates are almost always soluble, except for the bariums and the iron and so on. But the carbonate is almost always going to be insoluble unless it's reacted with ammonium or the group 1 elements. Well, this chromium is going to react with the carbonate. So it's going to be carbonate CO3. We'll balance the charges in a little bit. And then we have NH4SO. Right? Now we know this is going to be 2 minus, right? So this is going to be 2 minus. This is +1. So I need a 2 there, correct? We know this is +3. You know, that's 2 minus, right? So we know we need 2 of those and 3 of those. Bless you. Let's see. So if I do 3 of these, do those, that should be balanced, I think, is that correct? I think that's balanced. It's before 8 o'clock, it's just too stinking early, man. Make sense? Now, which was gonna be the precipitate? No, remember, all ammonium salts are soluble in water, so they're always gonna be, so this is gonna be the aqueous one, right? And then that would then be the solid, also, lanky. That's gonna be the precipitate. Just remember, always back, all ammoniums are gonna be soluble, they're gonna be soluble, they're gonna go in the solution. Oops. That makes sense? Any questions? Yeah. I'm deaf, I'm old and I'm deaf. What'd you say? Sorry. Oh, okay, how do I know, come up with the products I came up with? Okay, good question. So how did I come up with the products? Well, I know this is 3 plus, that's 2 minus, plus 1, 2 minus. This chromium is not gonna react with anything positive. They're gonna repel one another. Just like the sulfate is not gonna react with the carbonate because they're like charges, they're gonna repel one another. Opposites attract. Right? So and that's aqueous. That's aqueous. So these are all aqueous. So what happens is there are all these ions floating around in solution. Right? These are not bonded together. They're not connected together in the solution. They're floating around, but they're charged. So what happens is these two actually find each other. It turns out that when they're bonded, they're lower in energy. We're going to find out a little bit this semester, but quite a bit certainly next semester, that thermodynamics really matters. And so when these are going to be in solution, they're going to be at a much higher energy state apart than if they're actually together. So they find each other and they bond. That then reduces the energetics of the solution. It's a good question. Does that make sense? So, and it's always the same pattern. You're always going to have a cation, anion, and all you simply. I'm teaching my 11-year-old. Well, I've been teaching for a while though. I taught him when he was 9 how to do polynomials. Remember FOIL, first, outside, inside, last. So it's the same thing. You just come over to this, you do that. It's the same pattern every time. My son likes math. We do math. All right. The next one is what's the BA one called? That's barium nitrate, and that reacts with potassium sulfate. That's exactly right. Potassium sulfate. That's exactly right. So write the products for this, please. You get it? All right. So now we have the barium. It's going to react with the sulfate. And then the potassium to react with the nitrates. Now the barium is +2, that's -2, +1, -1. It just happen to be those charges. So everything is charge neutral, and now to balance it, we just put a 2 out in front of the potassium nitrate. Okay. Now, which one's the precipitate? Which one's gonna form the solid?
Barium sulfate.
Barium sulfate, yep, this one's gonna charge form the solid. And that was gonna be the aqueous. That makes sense? Yeah,
How do we identify them? Like which ones is influences?
so we memorize the solubility rules. There you go. Yeah, it's just there's a couple of things you have to, several things you have to be able to do these equations. One, you gotta know the polyatomics. You gotta know the name of the polyatomic, you gotta know the charge of the polyatomic, and you gotta know the constitution, how it's put together, right? That the sulfate is SO4 2 minus, nitrate is NO3. You gotta memorize it. You just gotta memorize it. If I give them to you, if I say to you, why don't we give them to you on a test? Zach, you're gonna say, I don't need this study, he's giving it to me on a test. So I don't, and I used to do that, and the grades were significantly lower. They didn't know how to do it. And it's like, someday I hope to own a tractor. But it's not gonna do me good to have a tractor, 'cause I don't know how to drive a tractor, but I want to own one someday, but I'll learn. So I force you to memorize those polyatomics. The second thing is, you gotta memorize the solubility rules. So I just memorized it. Do you have a question?
Yeah, is it always gonna be one aqueous and one solid solution, or is there any case that there could be two? I know there could be two aqueous because no reaction.
Exactly.
Is there any case that it's two solid, like could be two solids?
Oh, absolutely, yeah, you could do something like that, absolutely, yeah. Be kind of weird, but yeah, you could do that, absolutely. But for general chem one, if it's a precipitation reaction, we're just gonna have one reactant. Or I'm sorry, one that's gonna be precipitate, and one's gonna be aqueous, yeah. This, I don't. My goal is not to trick anybody, I really don't want to do that, I just want to test you on what would be appropriate for general chemistry. Yeah, yes, you could have that. Be weird, but you could have it. Good question, yeah, mhm.
If. Sorry, I'm trying to think of
That's
an
fine.
example, but like, if they're like, let's say there's a compound and none of it is on the solubility chart, do we assume that it's aqueous?
If it's on the reactant side, yes, but I'm not gonna ask you anything outside of that side, I'm not gonna ask you anything outside of this. I never have this, no, I would only ask you things, sir, I mean, we could get into the chlorates, hypochlorites, I'm not gonna do any of that stuff, we're just gonna do this is it, that would be for if you wanted to become a chemist and you would have to take an inorganic chemistry class, which we don't even offer here anyway, but that's where you'd learn it, but no, I would, this is it, this is all I want to test you on. There's a lot in chemistry, there really is a lot. I don't want to discourage you too much, actually at all, but chemistry just sort of does it. But yes, there, you could have possibly having two precipitates, and there are a lot more ions than this, a lot, but these are the ones that are the most common. But a lot of people forget this, the lab my wife worked in for her PhD, they were working with a lot of phosphates. The phosphates are a lot of times insoluble. This is before she got there, but she worked in a biology lab. Nothing against biologists at all. They're really smart people. Very smart. But they had forgotten that precipitates out with calcium. That's one where the experiments didn't work for a while. So a lot of times the stuff gets forgotten. All right, we're good with these. Does that kind of make sense? So you got to memorize the polyatomics, and you got to memorize the solubility rules. That's how you do these. All right. I don't know how you memorize. I sit and I write stuff down. How I memorize. Okay. Now we're going to talk about acids. We're going to look at the Arrhenius definition of an acid. There are 3 definitions of an acid. We'll talk about them in the second semester. We're just going to talk about the basic one, or the most simplistic definition of an acid. So an acid is going to be something that ionizes in an aqueous solution to form hydrogen, which is an H+ hydronium cation. So something real quick, just how do you identify an acid? how do you identify an acid? An acid has a H in it. And typically, it's gonna be written as a cation. So if you write HCl, that's going to be an acid. HBr, that's going to be an acid, hydrobromic acid. Nitric acid is an acid, right? So those are all going to be acids, and you can identify them because you have a hydrogen as a cation. Well, here comes the exception. Here's when you look at organic acids, so these would be inorganic. When you look at organic acids, this is acetic acid. And this is its structure. This portion right here, that's the acidic portion. So that's going to be the acidic portion. And this is going to be that acid. So this is what's called a carboxylic acid. And so it's a carboxylic acid. They're written a little differently. Now, this will be, I think, we may talk a little bit about formic acid, but this will be the organic acid that we speak most of, right? So you can identify an acid because it's going to have a hydrogen more than likely out in front. Okay, that's how you identify an acid. Once it's nice to be able to identify what compound you're looking at, because then you know how to treat it. Yeah, Logan.
For the acetate, is it always gonna be like that to the other way?
I always write it this way. The only reason I write this way is because this is the structure of it, and the structure becomes important to it. You can also write it this way. It can be written C2O4O2, but this can be a lot of things. It can be a couple other things. It doesn't have to be acetic acid. I could write this as an alcohol. As ethylene glycol, right? So it has the exact same formula as this. I always write it like this. The way I know it's acetic acid. Yeah, Olivia.
Acetic acid has two different formulas, and then acetate also has two different formulas.
Well,
Because I've seen acetate several ways. There's like
Yes.
C2H3O.
yes, yep. So you can write acetate, it can be written as CH3COO minus. I always write it that way. It can also be written as C2H3O2 minus. It's the same thing. I like writing it this way because I know exactly what it is. If you have, this is why I'm not an organic chemist. I could write this now. I think that's 1, 2. I guess I can't write this. That's me. I can't write it. Sorry. Oh, what is that? Right this way. Sorry, non-organic chemist. Yeah. We have a ketone that way. Same form, but it's completely different.
Mhm.
So. Anyway. I don't like organic. That makes, we go, this is how you identify the acids. You just want to get to identifying the acids. These are all going to be monoprotic because they have one proton, right? We can have diprotic. The sulfuric acid is a diprotic acid. Sulfuric acid is going to be your diprotic acid. It can give up 2 hydrogens. We will learn next semester that it can give up the first hydrogen very easily. That second hydrogen, it doesn't give it up as easily. That's what the double arrow represents. We will talk about the double arrow next semester. We'll spend a month on that. So, yeah, Logan.
So I know HSO4 is hydrogen sulfate, so is that what the extra H is there for? Tell you that it's not just hydrogen sulfate,
Extra H.
like the H2 instead of just.
So the H2 is because this is a +1 and that's a -2. So there's going to be 2 hydrogens for that -2 charge. And so what happens is is, well, just like I have written up here. This sulfuric acid, what happens is sulfuric acid will give up a proton, all right, completely give it up such that you don't have the sulfuric acid anymore. And what you have now is you have a hydrogen and then the bisulfate or the hydrogen sulfate. This hydrogen sulfate or the bisulfate can likewise give up a hydrogen and produce another acidic proton as well as the sulfate anion. However, this doesn't completely go, it doesn't go to completion. Some of the storage leaves. So the reason there's two hydrogens is because it's a -2 charge. Why that is. Makes sense? To help you out, is that what you're asking?
Yeah, I guess, like, my question was like, how can I tell if it's an acid or if it's just hydrogen sulfate?
Well, hydrogen sulfate, so this is, if we were actually to name this, this is actually dihydrogen sulfate.
Yeah.
All right. If we were working just with this would be not just hydrogen, hydrogen sulfate or the bisulfate. Whereas this would be dihydrogen sulfate or sulfuric acid.
Okay, okay.
Makes sense? Good, good, good. So for the most part, we're just gonna be working with monoprotic acids that are going to yield one hydrogen. One of the few exceptions will be the sulfuric acid. This is stuff that eats holes through clothes and all that. So the battery acid. Bless you. Okay. Now we have these things which are called strong acids. Now, strong acids would be such a hydrochloric acid or sulfuric acid in that if you have this and you put it in aqueous solution, it's going to completely be protonate. It's going to completely separate or come apart into the hydrogen, the hydronium cation, and the resulting anion. Same thing happens with sulfuric acid, except it's really only for the first hydrogen, not the second hydrogen. So this is one of those things throughout the year you want to keep in the back of your mind. We'll talk about it a little bit this semester, but we'll spend a lot of time talking about strong acids and weak acids when we get to the second semester. We'll spend an entire chapter, which will take us at least a week and a half to get through that. But these are going to be the strong acids. You have the nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid. You also have sulfuric acid, the first proton. You have the perchloric acid. They're going to be your strong acids. We deal very little with the perchloric acid. We don't. Matter of fact, I don't think I've ever done a reaction with that in my entire life.
Should we still memorize that one?
Yeah, memorize the strong acid. But here they're going to be the ones you use mostly are going to be the nitric acid, the hydrochloric acid, as well as the sulfuric acid. We'll use those in lab. A lot of the problems we do will deal with those acids. I think I've used hydrobromic acid maybe once in my life, maybe twice, and I don't even know if I've ever used hydroiodic acid.
So is acetic acid not?
No, that's a weak acid. Yep, it's a common acid. We encounter it all the time, but that would be considered a weak acid. And what I mean by that is if I have a 0.5 molar nitric acid, and we'll talk about concentration, whatever the concentration of this is, whatever I start out with, when this is in water, that's going to be the concentration of the H plus. If I have acetic acid, if I have a certain concentration of acetic acid, that is not going to be the concentration of the H plus. It's going to be something different because it doesn't completely break apart. And so in that case, strong acids are very nice to work with. They're very easy to work with. Doing the calculations of strong acids are very nice and easy to work with. Weak acids are not. We'll save that for the second semester. But they're really not. There's a little thing called an ice table. We'll do this ice table, and it really makes it a lot easier. A lot easier. Really nice.
So with bicarbonate, is bicarbonate anything?
It's actually a base.
So with that, that's just a total other.
Yeah, we'll get to that, Olivia. It turns out that it has a hydrogen in it, but it turns out it'll actually accept the hydrogen much easier than it'll give off that second hydrogen. Uh, we'll get, we'll look at the definitions of an acid or base. So right now we're looking at the easiest definition of an acid or base, and this is something that gives up a hydrogen. And then we're gonna define a base as something that gives off an OH. And that will be our definition. But there's three definitions for an acid and there's three definitions for a base. We're gonna look at the most specific, the easiest. Does that make sense? The most general, which is more difficult, we'll look at something that does not have a hydrogen in, and it's a pretty strong acid. Well, what's going on? We won't spend much time talking about that definition of an acid or base. Does that make sense? This is just general chemistry. That's called the Lewis acid, Lewis base. That's my favorite definition of an acid or base because it throws all kinds of things into the mix. It's kind of fun to work with. But we're just going to look at what's called the Arrhenius definition of an acid or base. And he was kind of an interesting guy. When he went to get his PhD, he went in to describe how ions separate, and he passed his PhD defense, but he got the lowest marks possible. He ended up getting a Nobel Prize for that work. Yeah. So, now we have weak acids. We have much more, a large number of weaker acids than we do strong acids. So sulfurous acid is going to be an example of this. Hydrofluoric acid is going to be an example of this. My favorite is formic acid. Any of you ever know where you find formic acid at? Have you ever been bitten by an ant bite? And it itches, right? Or it burns. The reason it burns is because an ant will inject formic acid into your skin, and that's what's giving that burning sensation. That's formic acid. That's the simplest of all organic acids. Hydrogen sulfide. Any of you ever smell rotten eggs? Nobody's ever smelled rotten eggs before? Oh, well. I have a funny story. You like stories? I won't say where I lived or what grade this was in, but I'll say when I was in elementary school, we'll leave it at that. I hung out with a friend, Cole. He was on the other side of the tracks, so we had a lot of fun. He was a great, he got in more trouble. Oh my goodness. We got in a lot of trouble. Fortunately, my parents just let me get in trouble. It was kind of fun. Anyway, he went out one day and found a bunch of goose eggs and stole them. And goose eggs are pretty big, and so he found them somewhere in April. They were still in his garage in August. It tells you about the type of house he grew up in. And we had a certain teacher we really didn't like. Let's just say they found their way onto that teacher's front door in the middle of the night. Oh my goodness, I can't tell you how bad that smelled. We just carried them. I can't imagine what it smelled like when they actually landed on their door. Come on, that's funny. I thought it was hilarious. My dad was a teacher, used to work with her. I told my dad what we did. He said, "Good job. I'd have done it too." The only time I ever got clothes hung was I was with Cole. We were running from the cops one night. It's the only time I ever got clothes hung. Sprinting as hard as I could and I hit a clothes. Yeah, I got up and I ran as hard as I could breathe. I was running as hard as I could because I did not want to get in trouble. We didn't get caught. Anyway, so hydrogen sulfide, rotten egg smell, right? I'm not your typical professor. I really am not. Then carbonic acid. Anybody know where this is found at? Any of you drink soda pop? Oh, sorry. Any of you drink what, pop, right? You call it pop here, is that right? Pop? Yeah, I call it soda where I'm from. Anyway, all right. So that would be the carbonation, the fizz in soda pop. That's also the result of the carbonation, any kind of carbonated drink. So if you're looking at beer, that's going to be carbonated. You look at champagne, that's going to be carbonated as well. So any kind of carbonation. is gonna be a result of carbonic acid. And what carbonic acid is H2CO3. And what that really is it's really carbon dioxide in water. That's really what it is. And so we'll talk a little bit about that. How they make that. We'll talk about Henry's law constant. We'll talk about dissolving gases into liquids. Kind of neat. Okay. And then anytime you deal with these weak acids, they're going to be in equilibrium. And we will talk about that in the second semester of Chem 2, or second semester. That would be Chem 2. We will spend a good month on chemical reactions that are in equilibrium. What I mean by equilibrium is that if you were to take sulfurous acid and put that into water, it doesn't completely dissociate. All right, so it doesn't completely dissociate. If we go up and look at the strong acids, they do completely dissociate. They're going to completely break apart, except for that second hydrogen on sulfuric acid. But we will not talk about, and acetic acid falls into the weak acids as well. And we will not talk about these until we get to the second semester, okay? We're just only going to work with strong acid. How do you recognize a base? Well, once again, we're going to look at the Arrhenius definition of a base. We're going to look at the Arrhenius definition of a base, and that a base is going to be something that's going to give up a hydroxide, an OH. Olivia asked me if we have a bicarbonate, is that going to be an acid? And actually, it's not. It's actually a base. Even though it doesn't have an OH, it is a base, but we'll talk about that definition in the second semester. How many of you have to take organic chemistry? Just a few of you, is that it? Most of you are HES majors, is that correct? If you want to get through organic acid and actually understand the why of organic acid, a big thing is knowing how acids and bases work. And you can look at all of organic chemistry, all of it, in terms of acid-base chemistry, every bit of it. And that's how I understood organic acid. That's how I understood organic acid or organic chemistry. So you can have a monobasic base, which is only going to yield one hydroxide. We are only going to be talking about strong bases in this class. And so really this gets down, if you think about this, you can think about this in terms of the solubility rules, correct? So are hydroxides soluble or are they typically insoluble? They're typically insoluble. Yeah, that's exactly right. So hydroxides are typically going to be insoluble, with the exception, if you go back here, with the exception of all alkali metals and the heavy alkali metals. So the alkali metals are going to be the first group. The alkaline metals are going to be group 2. So if we look at that solubility rules, when we look at these strong bases, the strong bases are going to be all the alkali metals. So that would be all the group 1 metals, and then all the heavy group 2 metals. Now, if you decide you are going to become a chemist and you start working, you start preparing solutions, certainly basic solutions, you'll find out that a lot of these are not all that soluble. Certainly the calcium hydroxide. If you throw calcium hydroxide in there, what you end up with is just a big white mess. It really isn't all that soluble. I think organic chemistry is one of the hardest classes I took as an undergrad. When went to graduate school, I did really well in that organic chemistry class. I got an A. I did a very physical organic chemistry class. But as I told you, I had to teach it once, and I taught it 3 times. And I got a book and it taught me organic chemistry. It is absolutely an amazing book. I can't recommend it enough. It's absolutely phenomenal book. One of the best books I've ever read. And it taught a hardcore P chemist organic chemistry. I really, it wasn't as mystical as I thought it was. We go to say on these bases. So how you identify a base is that you're going to have a hydroxide in it. And that's how you identify a base. You identify an acid because you have a proton, you have the hydrogen. You identify a base because you have this hydroxide. Does that make sense? And now these acids and bases can come together and they can form what's called a neutralization reaction. You can have an acid, in this case, hydrogen, and when they react together, they're going to produce a salt and water. Now, in this class and in this room only, a salt is not just sodium chloride. A salt is going to be any ionic compound, any ionic compound. So it's an acid and a base reaction is going to produce a salt and water, whereas a salt is going to be any ionic compound. Now, if you look at this, and this becomes kind of subtle. It's a very subtle thing. If we look at a hydrochloric acid, which is going to be aqueous, when we react it with sodium hydroxide, which is once again going to be aqueous, right? The chloride and the sodium go together, so we get sodium chloride, and that's aqueous, but then we form water. Now, this water is not aqueous, the water is actually liquid. So there's a phase change, there's something different that occurs here. So the spectator ions of this are only going to be the sodium and the chloride. So the net ionic equation is going to be this. Because there's a phase change. Because the H plus and the OH on the reactant side are aqueous. However, on the product side, they're now a liquid. So they're different. That makes sense? It's subtle. All right. So I want to write the products for nitric acid reacting with calcium hydroxide. Get it? So the nitrate and the calcium. And then next is going to be the water. Now, calcium is +2. Nitrate is -1, so we need 2 nitrates for that. Alright. So we have to put a 2 out in front of there. That gets us 2 hydrogens, 2 hydroxides. So we need to put a 2 there as well. And this will be liquid. So now here's our salt. And there's our water. That makes sense? Good?
How would this, like the state of matter be for a solvent? Would it,
Oh.
yeah,
It's the aqueous, sorry.
okay. I just wanna-
Yep, sorry. Yeah,
Okay.
thanks. The aqueous. Cause all nitrates are soluble in water. Soluble. Oops. Turn that. Oh, we good? Now, we can also get some that are gonna be gas forming. We've all done this experiment, all done this reaction. We take acetic acid and vinegar, react it with baking soda. And what we end up getting is we get sodium acetate, which is gonna be soluble. We get carbonic acid, which is soluble, or which is aqueous. Now the bicarbonate is gonna decompose into water and CO2, and so there we'll see the bubbles. Makes sense? We've all done that, right? Did this as kids. All right.
Does carbonic acid always separate?
Yeah. It's funny thing is, Olivia, if you want to go to Sigma Aldrich or one of these chemical companies, say, I want to buy carbonic acid, you can't buy it.
It's water.
It's just water and CO2. Yeah. You can't buy it. I had an inorganic chemist, amazing professor, who wondered if it doesn't, doesn't really exist in this form. I mean, if you really think about it, so you can't buy it. It's just so
Is that what you said is like in pop?
it's just so pop, yeah.
So it's hypothetically, it's like a can of pop carbonic acid or,
Yeah, it's in there. And all it is, this is all they do, right? So if you have your bottle, I'll tell you how they make this stuff. So if this is your bottle, right, your can, so what happens is if this is your liquid, right? If you ever notice if you have a carbonated drink, there's always some empty space in it. You ever notice that? And that's because this is where your liquid is. And they pump in CO2. And they put so much pressure, right? When you ever open a can of pop, you hear, what is that? That is so up here, this is called the head space. And they inject that with an excess amount of CO2 to force the carbon dioxide into the liquid. So they put a whole bunch in there saying you gotta accept it no matter what. And CO2 and water don't mix. They don't like each other very much because this is what's called nonpolar, and water is polar. And so what happens if you want something to mix with water, it has to be polar. If you want something to mix with carbon dioxide, it has to be nonpolar. So you're getting these two polar opposites, pun intended, to be forced to be together, and they're not. It'd be like a Michigan fan and a Michigan State fan having to sit together and talk about football and agree on. Make sense? So they don't mix. But you can force them to mix if you add enough pressure to it. And over time, if you open up if you have a can of pop and you leave it out in the countertop or outside for a while, what happens to the pop? It goes flat. What happens is that the CO2 finally gets sick and tired of the water and just leaves. Because the attraction between the water and the CO2 are no longer, it's not a very strong attraction. Does that help you out, Olivia?
yeah.
So that's what that is. So when you see those little bubbles in soda pop, those are bubbles of CO2. And they only like themselves. They don't like water. And that's why they're bubbles together, because they don't want anything to do with the water. They can't stand the water. So they all kind of crowd together and form those little bubbles, and eventually they eventually leave because they are not attracted to one another at all. That's what it looks like. I help you out. I have more information to carry now. It really neat stuff. It's really, really neat stuff. All right. I'm gonna introduce this. So now that you're comfortable writing chemical reactions and with charges, I'm gonna mess it all up now. Yay! Job security, right? Just kidding. There is this thing called redox reaction, so oxidation reduction reaction. We will talk briefly about this semester. We will talk about this for an entire chapter next semester. But this is what's called redox reaction. So this is oxidation is going to be loss of electron. Reduction is going to be gain of electron. So any of you who had this in high school chemistry, you may have heard this as Leo goes Gur. Anybody ever heard that? Leo goes Gur, and sometimes I have a little button on there. I remember seeing went to enough conferences that you would see high school teachers wearing little buttons with a line going Gur. I thought that was stupid. I was just I never really remembered that. I always remembered it as terms of oil rigs. I used to teach in Kansas for a number of years, and I learned that oxidation is loss of electron and reduction is gain of an electron. Okay. When those of you who, when you take organic chemistry, learn about this, you'll learn about it much, much, much easier. In organic chemistry, oxidation is gain of oxygen and reduction is loss of oxygen. Here we learned it as oxidation is loss of electron and reduction is gain of electron. And it's a little bit confusing at times because if we're losing an electron, we would think that if we're losing something, it would be negative. That's the opposite. Because what we're doing is we're actually losing something that's negative, so it becomes positive. Does that make sense? And reduction, you think, oh my goodness, reduction. Well, in this case, you're gaining something. Oh, well, I should be getting more positive. No, because you're actually gaining something negative, so the reduction is going to be more negative. So you think of this in terms of reduction is going to be a reduction in the oxidation or in the charge. If we look at magnesium, the charge of all elements, it doesn't matter where it is on the periodic table, the charge of all elements is always going to be 0. The only things that are charged are ions. Does that make sense? That's the only thing that's charged are ions. Elements are always going to be 0. So if we take magnesium, we react it with hydrochloric acid. What happens is that the magnesium reacts and produces magnesium chloride, and then the hydrogen reacts with itself to produce hydrogen gas. And I don't know why there's a 4 there. No idea where that came from. Okay. So if magnesium is 0, it comes over here and becomes magnesium 2 plus. Is magnesium oxidized or is it reduced?
Reduce. So that's confusing.
So are we gaining electrons or are we losing electrons when we go from 0 to +2? We're losing electrons. Actually, we're losing 2, so magnesium is oxidized. Confusing, right? Hydrogen here is +1. Chlorine is -1. We go from +1 over to something that's now 0. So if we go from +1 to 0, is it oxidized or is it reduced? It's reduced, yeah, because we're going more negative. So this charge is reducing in size, so it gets reduced. And nothing happens with the chlorine. In this case, it's -1, and over here it's still -1 again. So nothing happens with the chlorine. It remains the same. We good? Got that? Now, if that's not confusing enough, let's enter some. Let's bring in some more vocabulary. I think this is a vocabulary class. An oxidizing agent is something that becomes reduced, meaning the oxidizing agent is the one that gains the electron because it's the agent that causes oxidation to occur. So it is what removes the electron. Okay. A reducing agent is the species that becomes oxidized. It's the agent that allows, that thus takes. Or that gives up, that allows the other species to reduce. So it's the thing that gives up the electron. Does that make sense? We come over here. I'll go back that side. I promise. Over here, I'll just let you write.
What,
Yeah, absolutely. Norman.
how, yeah, it might just be. But how is the, I know like hydrogen's +1, right? I'm not sure idea, so how's one is bigger?
So in this case, it's 0 because it's elemental. And oxygen here is going to be elemental. When we come over here to water, the charge of hydrogen is going to be +1 because now it's reactive with something. And oxygen is going to be -2 because of where it's located on the
Yeah.
periodic table. So in this case, the hydrogen becomes +1, the oxygen becomes -2. That help you out?
Yeah.
Is that what you're asking?
Yeah.
Okay, good.
Then the hydrogen would be the one that is oxidized, but
Yep.
the oxygen would be the oxidizing agent. Okay,
Yeah, we'll write the whole thing out, okay? We'll get it all written up, we'll go through it all. Everybody got this written down? Okay, so if we look at hydrogen. So in that example. Hydrogen is going from 0 to +1, so it is being oxidized. All right? And it is. The reducing agent. Now, oxygen. Is being reduced. And it is. Oxidizing agent. That makes sense? Okay. So hydrogen is going to be 0 to +1. In order for it to go from 0 to +1, it had to have lost an electron. So anything that loses an electron, it's becoming more positive because it's losing this electron. So the hydrogen is being oxidized, okay? Now the oxygen is 0 in its elemental state. It's gaining electrons, so it's being reduced because reduction is gain of electron. So it's going to be reduced. Since the hydrogen is what's being oxidized, it is the reducing agent, meaning it's the entity that gives up the electrons to the oxygen. The oxygen is the oxidizing agent, and that is the thing that takes the electrons from the thing that's being oxidized. Yeah.
so the hydrogen only gave up one electron, how would the oxygen?
I have 2 hydrogens.
Oh,
There's 2 hydrogens. Yeah, 2 hydrogens give up. Yep. Each hydrogen gives up 1. So it takes 2 hydrogens to give up the 2 electrons for the 1 oxygen. Yeah, good question. Good question. That makes sense? We're good? All right. We will do this on Friday. How's that sound? All right, plan? All right. Have a good Wednesday. It's time to tomorrow. Goodbye. How you?
everybody else has a lot.
How is it?
Yeah. I like, I don't know.